So let's pick up where we went off. Any questions from last time, I guess? Could ask. Okay. All right. We've said that we're talking about control volumes. And our interest in control volumes is that we're dealing with conservation equations which are conserved inside some volume. We've defined control volumes in three specific ways, and it's perhaps useful to recap exactly what those are. And they are either static, where you have fluid going through it from one side to the other, and you can do the accounting on that. They can be moving, like a jet engine, where not only is the control volume moving, well, the control volume is moving relative to some flow, and the idea of a balloon flying around where not only is the control volume moving, but also the volume of the control volume, if you like, is changing. And so we'll use the concept of control volumes. We used it already with the idea of substantial derivative and the idea of relative velocities. And the example that we used to make the point, I guess, I think we have it here, it was this, right? Our trusty fireman's boat. Maybe I'll shut that off. And the idea was that it matters to us what reference frame we're choosing. And it matters if we're sitting on the boat and we're squirting fluid forward at 1 meter a second, then we see it going out of the boat at 1 meter a second. If we're traveling on the boat and it's also traveling in the same direction at 2 meters a second, then we still see it coming out of the boat at 1 meter a second. But if we're standing at the Statue of Liberty here and watching it, we'd see it going at 1 meter per second out of the boat, but the boat moving at 2 meters a second. And so it would be the vector sum of those two things that would describe how we saw it as a static observer. And so that's kind of important to us in how we deal with understanding control volumes. Because if we're using different reference frames, then we have to define our behavior in slightly different ways. And so we'll use this to maybe illustrate that. So you'll recall that we started off with Reynolds transport theorem, and we substituted in a value for mass that went in here. And using this expression here, we came up with the substitutions with something that looked maybe a little more palatable. And we tried to explain what that was in terms of kind of more concrete components. And we said that we could take this expression and we could modify it. You'll notice here that we've written this slightly differently in terms of this component W as a velocity in here. And we should define that. But let's not worry about it for the moment. But let's expand this as we did last time. And we can write this as, for instance, if we take the, differentiate this by parts, we end up with a density multiplied by a change in volume with time, plus a volume multiplied by a change in density with time, plus a mass flow rate equals 0. So this is maybe a more convenient way to write it. And an even more convenient way to write it in our shorthand is that we know that this can be written as a dot product. And so if we write this out as this, that's the way that we can think of this expression. We made the point that if mass flows in, then because of this idea, I should probably draw a figure to be able to demonstrate this. So we have this outward normal. if mass flows in, then it is what? Negative, because it's flowing in the opposite direction to the unit normal. And if mass flow rate is out, then it's defined as positive. And the reason for that is that this velocity here is defined relative to the outward norm, just as a convention. So as a sign convention in this expression, then mass rate is positive if it's flowing out, and it's negative if it's flowing in. And so that's part of the deal. And so this mass flow rate we can always think of as a velocity multiplied by a density and multiplied by an area. And so this here would be an area. And in this particular case, we've taken the velocity as equal to v. But that's not the whole story, and because the whole story depends on exactly what the control volume is doing. And so what we can do is we can think of control volumes in three different flavors, the three different flavors we talked about. One is static, that has stuff flowing through it, which is really kind of what we're talking about here. There could be fluid flowing in here and coming out the other side, which would be consistent with this. One is where this actual control volume moves as a velocity of the control volume, CV, but doesn't deform. And then also one where it moves, but it also deforms. And if it deforms, then it's not enough for us to talk about the control volume, which is this thing here. This is our dotted line around the control volume. We have to talk about a control surface. Because if we look at this control volume at time t, but then we look at it at some other time t plus delta t, whoops, then maybe this control surface, or maybe the control volume, looks like this. It's no longer the same size as this, it's changed size. And so this face has changed relative to this face, and so the control volume isn't constant, and so we actually have to tag ourselves to a control surface, CS. So that's the terminology we'll use. So that's the first part that we have to think about. The other part that's worthwhile thinking about is, I'm not sure what's going on in the background, is the idea of relative velocity. So in the same way that we take this, see if I can draw it, I've used this in other places, right? This is our boat. We're taking this boat as our control volume. Sorry. This is our control volume. And we could imagine that that boat is going at some velocity. We'll call either VCS or VCV. Let's do it control volume. Actually, let's do it as a control surface, because then that becomes good enough for everything. This is equal to the jet velocity. And so we can write this expression here, and I'll write it out, but this is the basic expression. It says that V static is equal to the jet velocity plus the velocity of the control surface, right? Makes perfect sense. We're squirting out at 1 meter a second. The boat's going at 2 meters a second. 1 meter plus 2 meters is 3 meters. That's exactly how fast we'd see the water going to a static observer. We have to set ourselves a coordinate system in Z. And we also have to realize that these really actually aren't scalar values, right? They're actually vectors. So if we wanted to, and we have this as equal to 1 meter a second, if the boat is going at 2 meters a second, then this vector here, which will have 3 components, is just going to be equal to the velocity in the x direction is 1 meter a second, in y it's 0, and in z it's 0. The velocity of the boat is equal to 2 meters a second, 0, and 0. Again, meters a second. And so by definition, this is 3, 0, 0. So we can think of it as scalars, but really they're vectors. They're vectors, but when we take this dot product, we talked about what this dot product meant. This dot product is really just the relative velocity across that surface. So although these are vectors, we have to write, well, I don't need to write it. This is W. Typically, since we're interested in how much stuff goes into the control volume, right? You know that this is physically coming out of the hose. You can think of this as coming out of the control volume. And so this is the parameter that we're interested in. And so probably we're interested in rewriting this equation as W is equal to V static minus VCS, which is just this expression that's rewritten. And all this is saying that since we do our accounting of flow into the volume, then it matters what direction we're going. So in other words, certainly if you have this cube that's moving in this direction at some velocity of the control surface, it really doesn't matter what the velocity of this control surface is if you know that it's coming out at some relative velocity W1. That's what we need. It's coming across that control surface. And if we know that relative to the amount that is going in, also at some different velocity, it only matters what the relative velocity is relative to that surface. It's kind of like the picture we took of the truck going off to the left-hand side, firing a cannon, the ball coming out at exactly the same opposite velocity to the truck. It looks like it's static. To the truck, all that matters is it comes out of the truck at the same velocity the truck's moving. It comes out of it. So it's the actual motion at which it comes out of the system. So this is what we're interested in. And so this is what goes into this expression here, as you'll see. So it's the relative velocity. And this is going to be V static minus V control surface, right? As a scalar. So hopefully that's not too complicated. But that's basically what we're attempting to do. And so all that matters is the relative velocity that comes out of it. And we have to calculate what that relative velocity is for the system. Okay. All right, so I think that's kind of the discussion that we've had here. So we'll do 3 cases, the 3 cases we talked about. Static non-deforming, moving non-deforming, and moving deforming in different regards. And so one way to look at that behavior is in terms of this movie. And so the simplest possible control volume we can imagine is something like this. I'll turn the volume off so we don't have to mess around with this. And so what we could do is if we wanted to evaluate that, then it's relatively straightforward, right? So let's get a piece of paper. Let's get this going here. Let's do this. let's have this. And so 6.3, conservation of mass is what we're doing. And so we can draw this system as being this. This is our beaker. This has a velocity, it has an area, it has a total area attached here, and if it has some kind of height to it, and we're interested in the question, how long to fill, then we can calculate that as being equal to the time to fill is equal to the mass that needs to fill it divided by the mass rate, right? Because this would be in kilograms, and it would be kilograms per time, which is just going to be time. So that's really all it is. And so if we know what this volume is, the volume is going to be equal to the area times the height. So what's the mass? Mass is just equal to volume times density, which is equal to area times height times density. And what's the mass rate? It's what we're calling m dot. It's going to be density times volumetric flow rate, and volumetric flow rate is just going to be equal to this velocity v1 times a1. And so if we want to calculate the time, I mean, we don't have to have this class to be able to figure out how long it takes to fill a bucket. You just look at the ratio of those, and it should be area times height times density divided by density times v1 a1. We lose the densities, and it's just area times height over v1 a1, whatever this is. Which is the same, of course, the same as saying this is just volume over flow rate. Right? Area times h is the volume, and this is the volumetric flow rate, because density doesn't change. So implicitly, we know how to do that. We don't need to know about conservation of mass or any of the complex things we talked about today to be able to do that. The other way we could solve that problem would be to do this. If we wanted another way to do it. Alternatively, and so what we could do is we could take this system and we could look at the bead of water which comes down to hit the bottom of the bucket. And instead of starting our calculations at time 0, which is now, just before I turn the faucet on, maybe we start our calculations at time a little bit later, when the bead of water has first hit the bottom. Okay? So we have this column of water, which is now hit the bottom of the beaker. And instead of taking our time 0 as when it first came into the beaker at this point here, we take time 0 at this point. And so that's kind of an affectation or an arbitrary choice, but it's useful because if we want to be able to use fixed moving and deforming control volumes for this problem, we should get the same result no matter what kind of conceptualization we use to solve it. And if we want to get the same result, we just have to use that conceptualization. So what we're going to do is we're going to do this. And so this is the fact that already having come down to this bottom is A1. The rest of the beaker is A2, so that together A1 plus A2 is equal to area. And so now if we do the same calculation, that time to fill it is equal to mass over mass rate, which is exactly the same as we've just written up here. No different than that. Then we can look at two different things. The first is, how long does it take to fill this bead here? So what's the mass going to be? The mass, oh, I guess we need this as well, right? Mass is equal to volume times density, which is equal to the area times the height, area 1 times h times density. The mass rate is equal to what? It's equal to A1 V1 times density. And so we look at the time taken to fill, which is equal to the mass divided by the mass rate. Then that's equal to A1 times height, which is the volume, times the density, divided by A1, velocity 1, and density. We get rid of those. Perhaps we leave it that way. I think there's a reason that we leave it that way. So that's the first stab at this. So if we look at now to fill the remainder, I'm going to come back to that. So to fill the remainder, again, mass is equal to what? Mass is going to be equal to this cross-sectional area. Mass is equal to volume times density, which is equal to A2 times h times rho. The mass rate has to equal what? There's no fluid coming in here, but there is fluid coming in through here. So the mass rate should be nothing different from before. It should be equal to the this is A1, right? Okay. So the mass rate is going to be equal to the area 1, its velocity. So this is equal to Q, right? And multiplied by density. And so if we look at the ratio of those, it's just going to be equal to A2 times h times rho divided by A1 times velocity 1 times density. And so all by way of saying is that if we look at the total time to fill this, then the total time to fill, if we call this 1 and we call this 2, or if we call this the column plus the bulk, then T total is equal to T column plus T bulk, which is going to be equal to these two added together. So hopefully this is right. A1, H, we don't actually need the densities. A1 V1, which is this. And hopefully if this is right, this is the other one. Get rid of these. Plus A1 V1 divided by A2H. And we have the same numerator in each case. And so in other words, we have A1 V1, you're probably ahead of me in this, A1 plus A2 times H. And this should be, hopefully, the same as this. So this is the expression we had before, and this is the expression we have now, where this magnitude here is just equal to the sum of those two areas. So this is the total area. So we have exactly the same expression. So we have the same system, and so either way we calculate it, it takes exactly the same amount of time to be able to do this. But the reason for splitting it out is that if we want to use control volumes to do these calculations, then we're going to take it that the bead of water has hit the bottom, and the rest of the time that it takes for it to fill up this column is going to be given by this expression for the bulk, A2H over A1 V1. Right? So all we've done is we've said we can look at it filling up the whole container, and we get an expression. If we divide that filling up of the container into two parts, that we fill up this column first, and then we allow the water to rise in the rest of the container, then we should have exactly the same time. And we've done it by figuring out how long it takes for the column to fill out, how long it takes for the rest of the bulk to fill out. You add them together, and this expression here is T total, which is exactly the same as we had before. And so this is the expression, if we use all these different control volumes, that will end up mimicking. So that's why I wanted to demonstrate the fact, no, sorry, this is the expression that will end up mimicking. The part to fill up the base. Okay? See how far we get with the other stuff. So, first idea, non-deforming but stationary. Same idea as what we've done already. We look at splitting out this. Let's look at the individual components of our conservation of mass term. We know that mass rate in is negative, mass rate out is positive. Just as a reminder to ourselves. Because that lets us take care of this particular term here. Not worry about it. So, change of volume of the control volume with time. So what we're going to do is we're going to take this as our control volume in the bottom. This bead of water will already have sunk down to here, so it'll have filled this up. And so if you think about our static and non-deforming control volume, it looks just like this at the bottom. This is this. And so on one surface it has some fluid coming in at some velocity v1, but it also has the water level rising at some velocity v2. So that's the way that we're dividing it. So this is on the left hand side, this is our bead of water coming in. This is the water level rising as it comes up above us. We have the area of the bead of water that drops to the bottom. We're ignoring the fact that it tapers because it accelerates. Don't worry about that. And we have this rising level. So what can we say? The rate of change of volume of the control volume. Well, it's a static, non-deforming control volume. If it's non-deforming, by definition, dv dt has to equal 0, right? Just by what you'd expect. So this is 0. It's at atmospheric conditions all the time. Pressure the fluid sees all the time is atmospheric. It's not a big pressure change. Even if it was a big pressure change on the liquid, it probably wouldn't change density very much. And so we're going to take that is 0. If it's a gas, it might be something different, but certainly we can do that. And so we can do the mass balance on a volumetric flow rate in, a volumetric flow rate out, and this is the water rising, and they have to balance each other. The amount going in has to equal the amount going out, otherwise it's going to net accumulate in this volume. And so let's look at what V1 is. V1 is into the volume. It's into the volume, and so it's negative. This is a scalar value. It will take as a scalar value, and it's multiplied by density. V2 is out of the volume, and so because it's out and it's also parallel to the outer normal, which is the reason that we get this definition here, this is positive. Flow rate times this. Cancel out the densities because we don't need them. We end up with calculating that the velocity just by rearranging this term in terms of V2. So if we rearrange this expression now with all the zeros in terms of V2, we get this expression here. And if we take the time that it takes to fill as being, we called it before, the mass divided by the mass rate. If we divide the mass by density and the flow rate by density, it's the same as the volume divided by the flow rate, right? Just a different way of doing it. It might have been easier just to do it as mass by mass. Yeah, okay. And if we do that, the total volume is going to be equal to this area A2 times the height. It has to fill up. And we know that it's going into that volume at a rate of V2 multiplied by its area. So V2 times the area is the rate at which it goes in. And so between these two, this is the time it takes to fill. And so the time it takes to fill should be exactly the same, hopefully, as this expression here. A2H over A1V1. A2H over A1V1. Same thing. So it's the same physical system. So that's one way of thinking about this. We could choose the control volume if you wanted to at the top, but we've chosen it just at the bottom. And we've looked at a flow in, a flow out, and the essentials of it are that because we're not allowing anything to accumulate here, because the density is not changing, and certainly the volume of this is not changing either, then we've ended up with a static control volume. So, a little bit of a contrived example to do it. We can do it with a non-deforming but a moving control volume. And if we do that, then we need to account for things in this particular way. We've made this point already, that we're interested in being able to look at the sum of these velocities. And this is what we're interested in, because this is what we have to account for going across that boundary. So typically we'd be interested in rearranging this as V minus velocity of the control surface. So this is static observer. The movement of the control surface. Actually, it's control volume, but the more complicated one is the control surface, so we can always think of it that. And this is the rate across the boundary, the volume, sorry, the velocity across the boundary. So you'll remember, right? So this is firing the gun, the hose at this velocity across this boundary. The fact that this control surface or control velocity, control volume, which also equals the velocity of the control surface, right? Because it's not deforming, it's not concertining. So every single point on this control surface is moving at the same velocity, right? By definition, because of this, it's not deforming. And this is what we're interested in doing the accounting on in this equation. And so if we think about that, so one way we can now solve this problem is to do this. So we'll take this as our control volume as before. This is at initial time 0. But what we do is we allow this control volume to go up at some velocity. And so at the next time increment, this control volume is going to look like this dotted line here. Hasn't changed size. Don't think it's changed size. It may look like it has because I can't draw very well. But it's just migrating up through the system. And if we want to do that, then one way that we can do it is we can just peg the top of this at the rising level. So as the water's rising in the beaker, then we tag the upper level of the water with this surface here. So this always becomes basically our free surface. And then that says something about the flow rate across that boundary. By definition, is going to be 0. Actually, we didn't say that here, right? But we should be looking at all of the boundaries here. The one thing I didn't mention was that this control surface, the velocity across this boundary is 0, and the velocity across this boundary is 0. It may have been self-evident, but we have to do that accounting as well. Those velocities are both zeros, and so in terms of these mass flow rates, they have to be 0 as well. If we use this non-deforming but moving control system, then that's no longer the case, right? Because this control surface is moving up at some velocity. It's going to be V2. And the fluid that it goes past is static. So it's going to be moving relative to that flow velocity. And so the basic idea of this then is to do this accounting again. So this is our expression that we've written out. If we write it out in shorthand, it's rho v dot plus v rho dot plus m dot equals 0. Volumes and densities. So again, the volume is not changing. Control volume. It's translating, but it's not changing. And so by definition, this term is 0. The density is not changing because the pressure is the same, and so we get rid of this term. So both of these two terms are 0. So the only terms that we have to do are the accounting on this. So now, if we look at this, I guess we could think of 3 different velocities. We have a velocity in here. We have a velocity at which the control surface is moving. And we have a relative velocity of a fluid coming out of the bottom, right? Because this is translating relative to the fluid. So this is going to be our W1. This is going to be our A1. This is going to be our A2. And I'm not sure whether we're going to get through this or not. I think we're not. And so we're going to have some fluid coming in on this surface W1, which is this. It's coming into the system, so it's negative. We're going to have some fluid going out this at W2. But if we peg this to equal the velocity of the surface as it's rising, then this has to equal 0, right? Because it's sitting on the surface and it's rising with the surface. And so this component here, by definition, has to be 0. But this surface now is moving up at this velocity v2. So relative to the water that's sitting there, which is stagnant, then if you're attached to this surface and standing on this particular point here and looking at it, it would seem that you're going up in an elevator and the water's static, or you could think of yourself as being static and the water going down at the same velocity that you're going up. And so this velocity here is the amount that's going out. And it's positive because it is going out. And so it gets a bit complicated in the accounting of this that we have to do, but that's basically the idea. We're out of time, but I will make the final point that if you go through the calculations, you end up with the time that it takes to fill up is exactly the same as if you had a static, non-deforming volume. And one final point is if you look at a deforming control volume, you can imagine it being attached to the bottom of the beaker and stretching up as the water level rises. And not surprisingly, if you go through it, you get exactly the same time to fill. So I'll leave it there. All right, thanks very much. Don't forget, no class Monday. There'll be a quiz online to get done by Wednesday. We'll have class on Wednesday again. Pick up your exams, and if you want to contest any of the grading, do it before next Thursday midnight when your other assignments are due. And I think that's probably it. Yeah. Great.